Welcome to our journey into the world of sorting algorithms. Today, we're diving into bubble, merge, and quicksort, three powerful techniques used to organize data in ascending or descending order. Let's start with bubble sort. Imagine a line of people holding balloons with numbers on them. Each person compares their balloon number with the next, swapping if necessary. This process is repeated until everyone has their smallest number at the front. A simple but effective method, though not very efficient for large datasets. Moving on to merge sort. Think of splitting that line in half and then in half again, sorting each smaller group before merging them back together. It's like organizing a deck of cards by repeatedly dividing and conquering. Very systematic. Finally, quicksort. Imagine choosing someone as a pivot, let's say the person with number 5, moving everyone smaller to one side and larger to the other. You then repeat this process for each half. This algorithm is incredibly efficient and widely used in real-world applications. Dive deep into these techniques, and you'll master them. Welcome to our journey into the world of sorting algorithms. Today, we're diving deep into three popular ones: bubble sort, merge sort, and quicksort. First up, let's visualize how bubble sort works step by step. Think of it like a bubble slowly rising to the surface. Each pass through the list moves the largest unsorted element to its correct position. Next, we'll break down merge sort recursively, seeing how it splits lists into smaller parts before merging them back together. Quicksort is next on our agenda, exploring its partition and conquer approach. We'll compare these algorithms in terms of efficiency and real-world use cases. Finally, you'll get a chance to test your knowledge with some code walkthroughs and a quiz. By the end, you'll have a solid grasp of how these sorting techniques work under the hood. Welcome to our journey into sorting algorithms. Today, we'll dive into three popular ones: bubble sort, merge sort, and quicksort. Bubble sort works by repeatedly swapping adjacent elements if they're in the wrong order. Imagine bubbles floating up a line of numbers until all are sorted. Merge sort splits your data like cutting a sandwich in half, sorts each half separately, then merges them back together, creating an elegant sorting dance. Lastly, quicksort is like picking out one pivot element and rearranging everything around it, dividing the array into smaller parts that get sorted independently. Think of organizing books on a shelf by first separating them based on size. Welcome to our look at the bubble sort algorithm. This is one of the simplest sorting algorithms that works by repeatedly stepping through the list, comparing adjacent elements and swapping them if they are in the wrong order. Let's break down this code. The function takes an array. It starts with a loop that runs from 0 to n1, where n is the length of the array minus 1. Inside this outer loop, we have another loop that goes through each pair of adjacent elements. If the current element is greater than the next one, they are swapped using Python's tuple unpacking trick. This process repeats until the list is sorted. Bubble sort has a time complexity of n squared, in the worst case, making it less efficient on large lists compared to more advanced algorithms like merge sort and quicksort. Welcome to this tutorial on bubble sort. On the screen, you see an example of how it works. We start with an unsorted list: 64, 34, 25, 12, 22, 11, 90. The function iterates through the list multiple times, comparing adjacent elements and swapping them if they are in the wrong order. Each swap is visualized as an iteration, showing how the smallest numbers bubble to the top. After running this code, our sorted list will be printed out. This process might look similar for merge sort and quicksort, but each algorithm has its own unique approach. Stay tuned to see those in action next. Welcome to our look at the merge sort algorithm. Imagine you have an unsorted list of numbers. The first step in merge sort is dividing this list into halves, then each half again until we end up with sublists that contain just one element. It's like splitting a big problem into smaller, manageable pieces. Now, these single-element sublists are compared and merged back together in order. Let's dive into the code. First, it checks if the array has more than one item. If so, it splits the list down the middle. Then, recursively sorts each half before merging them back together with a comparison process that ensures everything is in order. Welcome to our tutorial on sorting algorithms. Today, we're diving into the merge sort algorithm. On this slide, you'll see how it works through its output. The function starts by recursively dividing the array into halves until each element is in its own subarray. Then, these subarrays are merged and sorted during each recursive call. Let's look at an example. We have an array 64, 34, 25, 12, 22, 11, 90. When we run the merge_sort function on this array, it gets broken down into smaller parts, sorted, and then merged back together. The final result is printed out: 11, 12, 22, 25, 34, 64, 90. Notice how the larger subarrays are gradually built up from smaller ones until everything is in order. This process makes merge sort incredibly effective for large datasets. Welcome to our quick sort code example. This algorithm is all about choosing a pivot element from the array, then partitioning the rest of the elements into two parts, those less than the pivot and those greater than it. Let's dive into the code. If the array has one or no elements, we simply return it as is. Otherwise, we pick our pivot. Let's say it's the middle element. We create three lists: for elements smaller than the pivot, for equal ones, and for greater elements. Then, we recursively sort the n parts and combine them with the voila! That's quick sort in action. Alright, let's dive into the quick sort output. In our function, we start by selecting a pivot element and partitioning the array around it. This means elements less than the pivot go to its left, and those greater go to the right. Then, the function recursively sorts these subarrays. For example, if we run this code with the array 64, 34, 25, 12, 22, 11, 90, the function will first pick a pivot and partition the array. Then it will sort the elements on both sides of the pivot. Finally, we print out the sorted result. Quicksort is known for its efficiency in many cases, but remember, it can degrade to O(n) squared if the pivot selection is not optimal. Welcome to our comparison of three popular sorting algorithms: bubble sort, merge sort, and quick sort. First up is bubble sort. While it's simple and easy to understand, its time complexity is a bit disappointing: O(n) squared in the best, worst, and average cases. That means for large datasets it can take a long time to sort. Now let's look at merge sort. It's more efficient with O(n log n) time complexity, making it much faster on larger lists. Plus, it's a stable sorting algorithm, meaning it preserves the relative order of equal elements. Finally, quick sort offers average case efficiency with O(n log n), but in the worst case scenario, it can degrade to O(n squared). Both merge and quick sort are generally preferred for larger datasets due to their better performance. Alright, let's dive into a real-world example to see sorting in action. We've got a list of student records. Each record is a dictionary with keys, name, and score. Our goal is to sort these students based on their scores. Here's the code. We define our list of dictionaries called, then use, which could be any sorting algorithm like bubble sort, merge sort, or quick sort, with a lambda function as the key to sort by score. The output: a new list where each student is now in order from highest to lowest score. Check it out. Alice comes first with 98 points, followed by Bob and Carol respectively. This example illustrates how sorting algorithms can be applied to practical data structures like lists of dictionaries. Let's see how this code works. We have a list of student records in dictionaries format, each with a name and score. Our goal is to sort these students based on their scores from highest to lowest. The function does the heavy lifting here by using the merge sort algorithm. When we run the print statement, it outputs the sorted list of dictionaries. For example, Alice with a perfect score of 98 comes first, followed by Bob with 87, and then Carol with 76. This demonstrates how sorting algorithms like merge sort can efficiently organize data in real-world scenarios. Alright, let's put your sorting knowledge to the test. We're looking at three popular algorithms: bubble sort, merge sort, and quick sort. So, which is best for large datasets? Let's break it down. Bubble sort? Not a good choice. Its time complexity of O(n squared makes it inefficient for larger lists. But what about merge sort and quick sort? Both shine with their O(n log n) average case performance. That means they handle big data much more efficiently, like a breeze compared to the clunky bubble sort. So, when you're dealing with large datasets, think merge sort or quick sort. Your code will thank you for it. Welcome back. When choosing the right sorting algorithm, there are several practical considerations to keep in mind. First, consider your dataset size and memory constraints. For instance, bubble sort is simple but inefficient for large datasets due to its high time complexity. Next, think about stability. Merge sort maintains relative order of equal elements, making it stable, whereas quick sort can be unstable if not implemented carefully. Lastly, evaluate the presence of pre-sorted or nearly sorted data. In such cases, algorithms like insertion sort perform much better than bubble sort or quick sort. Remember, the right choice depends on your specific needs and constraints. Welcome back. Let's wrap up our discussion on bubble sort, merge sort, and quick sort. First, bubble sort is simple to understand and implement, perfect for small or nearly sorted datasets, but it's not efficient for larger ones due to its O(n)² time complexity. On the other hand, merge sort stands out with its O(n)log(n) time complexity, making it very efficient and stable. It's great for handling large datasets smoothly. Lastly, quick sort generally performs well, especially in average cases, but can degrade to O(n)² if the pivot selection isn't optimal. Understanding these differences will help you choose the right sorting algorithm for your specific needs. Welcome to our tutorial on common mistakes in sorting algorithms. Let's dive right into it. First up, using bubble sort for large datasets. Definitely not the best choice. Bubble sort is great for small lists or teaching purposes due to its simplicity, but it's incredibly inefficient for larger sets because of its O(n)² time complexity. Picture a classroom where everyone needs to line up by height. If you have just a few people, bubble sort works fine, but with hundreds, it would take forever. Now let's flip the script. When dealing with small or nearly sorted data, merge sort and quick sort are your friends. Both these algorithms can handle larger datasets more efficiently, thanks to their average time complexity of O(n)log(n). Imagine you're organizing a small bookshelf. Quick sort or merge sort will get it done much faster than bubble sort. Alright, let's dive into our quick sort quiz. You've got two options, O(n)² and O(n)log(n). Now, remember, quick sort is known for its efficiency in the average case. But why? Well, imagine you're sorting a bunch of cards. In an ideal scenario, each card splits your deck into roughly equal halves every time. This means, on average, you'll be dividing the list many times, leading to a logarithmic number of steps, hence O(n)log(n). However, there are cases where quick sort can degrade to O(n)², like when the cards are already sorted or nearly sorted. But in general, we expect it to perform exceptionally well. So which one is correct? That's right, O(n)log(n), the average case time complexity of quick sort. Alright folks, let's wrap up this journey through sorting algorithms. We've covered three main players, bubble sort, merge sort, and quick sort. Each has its own strengths and weaknesses. Bubble sort is simple but inefficient for large datasets. Imagine trying to sort a library of books by gently swapping each pair until they're in order. That could take a while. On the other hand, merge sort and quick sort are more efficient, especially for larger lists. Merge sort splits the list into halves, sorts them separately, then merges them back together. Think of it as dividing your tasks to get everything done faster. Quick sort uses a pivot to split the data, making it super fast in practice, but can be less predictable. The key takeaway? Know your dataset and choose wisely. Whether you're sorting emails or organizing a massive database, picking the right algorithm makes all the difference.